the slope at x equals -3 is 0. Because if you look at the points to the left and right of -3, they are also at y equals 3. So if you go about finding your slope the old way, you get m equals 3 minus 3. And you could have looked at -3, -1, which gave you 0 over -4. Or sorry, -2. Which would give you 0. Part B, what is the slope of the value at x equals 0? So once again, you want to find the slope around 0. So you could pick the point -1 and pick the point 1. So you have 1, -1. So that's like -1 minus 3 over 1 minus -1. So you get -4 over 2 or -2. At 2, once again, you could use the point 1, -1, and we could use the point 4, 0. So it's 0 minus a -1 over 4 minus 1. Or you get 1/3. And then at 6, so this is a quadratic. It's a little bit harder to find the slope. We know that if we pick the point 5, 1, and maybe you pick the point 7, -3, it's going to be close, but definitely not identical. So we call this an estimated slope. Okay. So what about finding the slope of a function at a point is super helpful to us. So what we're going to do is actually look at a visual representation of this on Desmos. So your notes are going to kind of walk you through it while I visually take you through it. Give me 1 second. Okay. There we go. So we have this graph, and it is representative of our function. And what we want to do is look at this graph and talk about, okay, what is happening? What are we looking for? And how can we kind of compute what we're talking about? So we have f of x equals x squared minus 4x plus 4. And then we have different values of a and h. So as I move my h value, currently my h value is at 5.6. So currently my h value is at 5.6. If you think about the equation we've been talking about slope, where slope is the comparison of 2 points. So this is like your y2, your y1, and the difference between them. So in this case, the difference between them is 5.6. What happens as I take the difference between them and make it smaller? So now the difference between them is 3. So what did that do to my function? Well, here's my equation of a tangent line. Here's my slope of the secant line. And the red graph is my original. So did the purple line start to get closer to the green line? Not really. What happens as h gets even smaller, like 1? Yeah, so the green line got closer to the actual graph. Yep. Let's keep going. So as I keep changing it, what's happening to my green line? Yep. So as the green value gets closer and closer, as the h value gets closer and closer to 0, the green line gets closer and closer to the actual slope. Okay. So that green line's representative of our slope of our secant. And as we can see, if our h value gets smaller and smaller and smaller, our graph gets closer and closer to what we are hoping for. So going back to our notes, given that function, if we find the slope of the function at the point 3,1, what is the equation of slope again? So what's our equation for slope? Just in general, slope is what? How do you find slope of anything? Exactly. Or in this case, how did we find it in all of the warm-ups? We compared 2 points. So our equation for slope is simply a comparison of 2 points. And then in that Desmos activity, as we worked through it, we altered our point so that it was 8 units away from our given point. So our given point was 3,1. Our point on the graph that we were moving that green line was like 3 plus h and f of 3 plus h. So if this is like my x2, y2, this is my x1, y1, my equation for slope became y2, which is f of 3 plus h, minus y1 over x2, which was 3 plus h, minus x1, which was 3. And where did this 1 come from? Well, that's f of 3. So what does that look like? Hopefully this should look like the slope of the secant equation to you. Let's clean it up algebraically. So that's 3 plus h squared, because our original equation is x squared, minus 4 times 3 plus h, plus 4 minus 1 all over, well, 3 plus h minus 3 is h. FOIL out 3 plus h squared, so you get 9. 3h plus 3h is 6h plus h squared minus 12 it's okay. I just did the clear button with my finger. Minus 12 minus 4h plus 4 minus 1 all over h. Nine minus 12 is negative 3. Negative 3 plus 4 is positive 1. 1 minus 1 is 0. So 9, negative 12, positive 4, and negative 1 all cancel. That leaves h squared plus 2h, because 6 and negative 4, all over h, which gives h plus 2, because I can factor an h out of the numerator, canceling with your denominator. So what that means is that the slope, h units away from 3, is represented by h plus 2. So if I move that second point closer and closer and closer to the point 3, 1, that makes the h value closer and closer and closer to 0, which is really like saying the limit as h approaches 0 of h plus 2, which is like saying the slope of the tangent or the secant at 3, 1 is estimated to be 2. The slope of the function at that point is estimated to be 2. So another way of saying that we've been saying is that the slope of the tangent at 3, 1 is 2. In fact, limits of the form previously talked about in Chapter 2 arise so frequently in calculus that we call them the derivative. Limits of the form happen so often in calculus that we call them the derivative. The derivative of a function f with respect to variable x is given by f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. The derivative, also known as f prime of x, is given by the equation the limit as h approaches 0 of f of x plus h minus f of x all over h. The rate of change of a function is the derivative. The rate of change of a function is the derivative. So we have some facts about f prime. The domain of f prime is the set of points in the domain of f for which the limit exists. It may be smaller than the domain of f, but can never be larger. The domain of f prime cannot be larger than the domain of f. If the derivative exists, then we say that f has a derivative at x, or you will hear me say f is differentiable. If f prime exists, then f is differentiable. A differentiable function is a function that is differentiable at every point of its domain. If we call something a differentiable function, then it is differentiable at every point of its domain. There is many different ways to write the notation for a derivative. The most common is f prime of x. However, you will often see dy dx as well. The directions of a problem asking you for a derivative may look like d dx of f of x. So again, the directions asking you to find a derivative might say, find d dx of f of x. It's not going to come outright and say the derivative of f at x. WRT stands for with respect to. WRT stands for with respect to. We say y prime or f prime of x because that stands for the first. So prime is kind of like first. So it's the first derivative. If you were finding a second derivative, you would say y double prime. So the second one, dy dx, that's how you'll say it. You'll hear me say dy dx or derivative of y with respect to x. We're going to get to a unit called implicit differentiation. Our denominators are not always going to be a dx. There will be times where our denominators are dt, standing for the derivative with respect to time. So in physics, if you had a function s of t, then that would be d dt of s of t instead of d dx of f of x. So whatever is in your denominator is what you are deriving. Whatever is in the denominator is what you are deriving. Differentiation is an operation. Differentiation is an operation. It is the operation of finding the rate of change of a function. Differentiation is an operation. It is the operation of finding the rate of change of a function. It is important to understand conceptually that the derivative represents the rate of change. So when I ask you to differentiate or find the derivative of f of x, I am asking you to find the slope of the tangent line or the slope of the function f of x. In this case, you are finding the slope in general because it's not at a particular point. So in example 1, we are finding the slope of x cubed for any x value on that cubic function. So we are going to find the slope for any x value on that function. So we say that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, where f of x is x cubed. So this is where something called Pascal's triangle is extremely helpful. So Pascal was a mathematician who liked to look at nature, and he discovered that in mathematics, the behavior of functions was similar to the behavior of exponential nature values. So Pascal said if something is 1 to 1, then the top of the triangle is a 1. He said that that triangle could expand so that the outsides were always 1s. And that if you added to get the middles, those 1s, then the triangle continued exponentially. So outsides are 1s. To get your middle value, you had to add the 2 last outsides, and you got 2. In our new row, he said, okay, outsides are 1, but I'm going to get some new values. So 1 plus 2 is 3. 2 plus 1 is 3. So as my rows expand, the insides come from adding the other insides. So then you add the outsides as 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And this triangle could continue on and on and on and on. So why do I care about this triangle now? Well, these 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, they represent the continuous coefficients of x plus h squared, or cubed, or to the 4th. So this first row here represents x plus h. Well, that's hard to see. The next row represents the coefficients of x plus h squared. Meaning if you expand x plus h, the coefficient of x is 1, the middle terms is 2, and the last term is 1. If I were to expand the cubic, x plus h, my coefficients would be 1, 3, 3, 1. Where the exponents go high to low and low to high. So let's look at the expansion of x plus h cubed, since that's going to be helpful in this problem. The expansion says that this is 1x cubed plus 3, and then it decreases by 1, x squared, plus 3 decreased by 1 to x, plus 1 decrease x by 1, x goes away. H in reverse starts low and goes high, or you can think that this is h cubed at this end, then h squared, then h, and then h of 0, which is 1. So the coefficients increase and decrease in opposite order, meeting in the middle. You can use this for any type of function. So if I were to look at, and I know we're going on a little tangent, but this is helpful to you. What if instead of x plus h, it was 3 plus h cubed? Those same rules apply. The coefficients are 1, 3, 3, 1. The first term goes from cubed down. So this is like times 3 cubed times 3 squared times 3 times nothing. And in reverse, times h cubed times h squared times h times 1. So 3 plus h cubed, without having to FOIL 3 plus h twice and then FOIL it again, is 27 plus 27h plus 9h squared plus h cubed. So if you can memorize and use Pascal's triangle, it eliminates the need to actually multiply 3 plus h times 3 plus h times 3 plus h, which again you could see would give you 9 plus 3h plus 3h plus h squared. And then you'd have to multiply it again by 3 plus h. And what you'll notice is that's 6h. So you can see 3 times 9 gave you your 27, 18h plus 3h squared. And then distributing that h gave you 9h plus 6h squared plus h cubed. And if you combined like terms, you had 27, 27h, 9h squared, h cubed. So Pascal's triangle kind of eliminates the need to FOIL multiple times. So using that idea of Pascal's, we can now say that the limit as h approaches 0 becomes x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h without having to FOIL the problem. We notice that the x cubes cancel. I can factor out an h. So it becomes 3x squared plus 3xh plus h cubed all over h. The last one's h squared, yes. Sorry, it's a little messy. So you can cancel your h. And that leaves you with the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Plugging in your 0 for h. We're left with 3x squared. So what that means is that the derivative of x cubed is 3x squared. And I know all of you in physics are like, I hate you, Mrs. McBride. I could have done that in one simple step. We will get there. I believe that's 3-3 is the power rule. Section 3-3. So this is 3-1. We got 2 sections to go. What? No. It was just kind of like one of those things that I was teaching you. I have no idea what you just mumbled. I'm sorry. There you go. Yes. Guys, you must have the limit as h approaches 0 at every line until you plug in 0. Otherwise, mathematically, it's a lie. The only thing I hate about masks is I can't understand the mumbles. I have good ears and I cannot understand the mumbles. I know, but like usually I can decipher them because I've like listened to kids for so long. But now like we're facing the opposite direction, so I'm really hurting to like understand. Which we might not be facing opposites for long. We might be moving to the math lab. I may have no choice but to move my classroom there. Brooke, you good? Yeah, that's not good. I mean, you can take pictures of my board and then turn it into a printable PDF. I'll just go over the PowerPoint. It's okay. Not fun. All right, differentiate the derivative x squared minus 8x plus 9. So you have the limit as h approaches 0 of x plus h squared minus 8 quantity x plus h plus 9 minus x squared plus 8x minus 9, distributing the negative in all over h. Leaving x squared plus 2xh plus h squared minus 8x minus 8h plus 9 minus x squared plus 8x minus 9 all over h equals the limit as h approaches 0. Simplifying out, you get rid of your x squareds, your 9s, your 8x's, so that leaves 2xh plus h squared minus 8h all over h. Each term has an h, so we take it out. Leaving the limit as h approaches 0 of 2x plus h minus 8, making your derivative or slope 2x plus 8. So again, that represents the derivative, which represents the slope of the tangent at any x value. Sorry, it should be minus 8. Okay. So that represented the slope in general. There is a modified formula for finding the slope or the derivative at a point. So the derivative of a function f at a point, x equals a, is the same as saying f prime of a for the limit as x approaches a, for f of x minus f of a all over x minus a. This is referred to as the alternate form of the derivative. So the derivative at a point is known as the alternate form. So your textbook, worksheets, etc. might say find the derivative using the alternate form, and that's this equation right here. So the other equation is known as the difference quotient. This is known as the alternate form. So we can use the alternate form to find the derivative at a point. And if you notice, this f of x should look familiar, as is the point we're finding it at. So we say that f prime of 3 is equal to the limit as x approaches 3 of f of x, which is x squared minus 4x plus 4, minus f of 3, which is 1, all over x minus 3. Because again, it's f of x minus f of a all over x minus a, where in this case, f of a is f of 3, which equals 1. So that becomes the limit as x approaches 3 of x squared minus 4x plus 3 all over x minus 3. And we know that if we plug in 3, we get 9 minus 12, which is negative 3, plus 3, which is 0. 3 minus 3 is 0. So we get 0 over 0 when we find the limit by direct substitution. So we know if we get 0 over 0, that's the indeterminate form. If you get the indeterminate form, that tells you algebraically you can do something to clean this up, which is to factor the numerator. So we get x minus 3 over x times x minus 1 all over x minus 3, which gives the limit as x approaches 3 to be x minus 1, which means this is equal to 3 minus 1, or 2. Which again, we're saying f prime of 3 equals 2, which means that the slope of the tangent at x equals 3 is 2. This is why, or this is an example of where what you know in physics will not help you. The power rule does not work for 1 over the quantity 1 plus x squared. So to find f prime of 2, we're going to do the limit as x approaches 2 of f of x minus f of 2. So it's kind of helpful to know what f of 2 is. In this case, it's 1/5 all over x minus 2. So now we're just going to clean that up algebraically. One over x plus 2. Let me see if that's my next slide. So just skip your example 2 or 3. Just skip a slide. Just go down to this example for now. I can always go backwards for you. No, we don't have that one at all. We have the right example 4. Oh, that's yeah, okay, then just like change your function as like yeah, I changed your notes a little bit this year. Okay. So we know that in order to subtract fractions, they have to have a common denominator. So that means I need the least common multiple, which is 5 times quantity 1 plus x squared. So we're going to multiply top and bottom to get them to match. So the first term needs the 5. The second term needs the 1 plus x squared. And all of that's still over x minus 2. So 5 minus 1 is 4 minus x squared all over. We know that if we have a fraction and a fraction, you can multiply by the reciprocal of the denominator. So that would cancel, and that puts the x minus 2 with this. So you get 5 x minus 2, 1 plus x squared. Hopefully you recognize that the numerator is a difference of squares. So that could be rewritten as negative 1 times x squared minus 4 which gives the limit as x approaches 2 of negative 1, x minus 2, x plus 2, all over 5, x minus 2, 1 plus x squared. We can cancel our x minus 2's, plug in our 2, and you get negative 1, 2 plus 2 over 5. One plus 2 squared. Two plus 2 is 4 times negative 1 is negative 4. 1 plus 2 squared is 5. 5 times 5 is 25. So we see that f prime of 2 is negative 4/25. So again, that means that at 2, the slope of the tangent is negative, which means that the graph is decreasing. So I know how much we adore word problems. A train is traveling back and forth on an east-west section of a railroad track. The train's position is measured in feet, given by the function x of t equals 5t squared minus 3t. Find the instantaneous rate of change of this train at 2 seconds. So really, what does that mean? Instantaneous rate of change implies the derivative at 2 seconds tells you the position or the time you're finding the derivative. So really, this question is asking me to find x prime of 2. So, do you want to use the original form or the alternate form of the derivative? Both will work. Okay? So that would be the limit as, the limit as x approaches 2 of f of x, or x of t in this case, minus f of 2, which is the same as x of 2. So 2 squared is 4. 4 times 5 is 20. 20 minus 3 times 2, which is 6, gives 14. All over t minus 2. Which gives the limit as x approaches 2 of 5t. We're hoping it's t minus 2 as a factor. So what I like to do is put in the t minus 2 and kind of work backwards to see if I can get that. So to get negative 14 times negative 2, you need a positive 7. So 5t times t is 5t squared. 5t times negative 2 is negative 10. Negative 10 plus 7 is negative 3. So that works. So then I get the limit as x approaches 2 of 5t plus 7, which is 5 times 2 plus 7, or 17. Which means x prime of 2 is equal to 17 feet per second. And again, I got the units from the idea that the limit up top was feet, and down here is time. Change in x over change, or change in y over change in x. It's the change in position over the change in time, which is how you get your units of feet per second. Okay, the next part is tomorrow then. Your homework is on that front of your packet. It tells you what to do for today. So make sure you accomplish the goals for Tuesday.